Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we're actually going to implement the quad trees. So we saw in our last video how a quad tree was this spatial data structure where we divide the region into 4 children. So we have a tree. Every node has, 4 children unless it's a leaf. And things are divided up based upon how many points there are in that area. So for example, if I add more points in here, we can make these things split up further, and this allows it to be adaptive so that regions of low density don't have a lot of boxes in them and the regions of high density do. Now we want to implement this. So we'll come back to Eclipse and we'll go ahead and implement our new Scala class, a quad tree. As with the grid neighbor finder, it turns out that our quad tree is only going to work for a 2-dimensional space. We'd have to implement an octree, which is going to be distinctly different, to get a 3-dimensional space. And how is this going to work? Well, it turns out that some of the code that we used here we're going to need as well. For the quad tree, we need to have information about the minimum and maximum value because the quad tree starts off with bounding the entire space and then it does the subdivisions. But we're going to make it square. It's easier if we only have one size variable instead of having one for x and one for y. So I will go with actually, we can do this in our next call. So the root will be equal to make tree, and make tree we're going to pass it the points that are going into the tree. We're also going to pass it the center location in x and in y, as well as a size variable. And so the center location is going to be 0.5 times min x plus max x, so that's the average value in x, and 0.5 times min y plus max y. And then our size value is going to be max x minus min x max y minus min y. So I want the larger of the two differences. I also need to bring across our visit neighbors. And now we need to define that make tree function. So make tree takes a sequence of type A. I'll just call it P. It also takes a CX, which will be a double, CX for center X, CY, which will be a double, and a size, which will be a double. And this is going to return to us a node. Well, if it's going to return to us a node, we better define the node type, which we don't have yet. So let's go ahead and let's create a class called node. What do octree nodes need to store? Well, it turns out they need to store the CX, the CY, and the size. So how about we throw those into here? Val CX is a double, val CY is a double, val size is a double. And I'm going to make it so all of our nodes have a have data in them and also have the 4 children. So children is going to be an array of node, except I'm not going to pass this in, sorry. Let's put val children is going to be an array of node. And we'll come back to that in just a second. And then val points is we'll just go with a sequence of A. Okay, and because we kind of don't like to have nulls, we'll go with making that empty, and by default our array will be an array of size 0. Okay. Though if we do this, both of those will have to be vars. Okay, so the way that we make the tree, this is actually going to be a recursive function. Make tree is going to call make tree on the various children. The other thing that I need to specify here, so in my example, I had it so that we only allowed 1 point per cell, and if I put a second point in here, it had to split things down. In practice, it doesn't always go down to just 1 point. A lot of times you'll want to have 3, 5, 7, somewhere in that range, probably single digits. In order to know what works best, you'd have to do some empirical testing. But I am going to go ahead and declare a val of max points, and I'm going to set it to 3 in this example. And so our points will never be larger than that. But that gives us our base case for make tree. If p dot size is less than or equal to max points, then we can simply return a new, actually this is going to take me 2 lines to do, val in equals new node of cx cy size. We're going to return in at the end, and in dot points equals p. Else, so what if we're not in that base case? Well, that means that this has to split into children, and so we need to make those 4 children. So we'll go ahead and we'll make a node. In fact, since we're doing this on both branches, I can go ahead and put that there. And since this in is going to be returned on both branches, we can go ahead and return in. So the only difference here really is what happens in between. And for the first one, we set it equal to, we just set the data to points. For this, because we're on an internal node, points is going to remain an empty sequence, but we need to set children equal to something. So children equals, equals array sub, and I'm going to go ahead and break this across. So that should be in.children. Break this across a few lines. So we need to pass in 4 children here. So these are going to be made with 4 recursive calls, make tree, and then we're going to need something for the sequence. We're going to need something for the center x, the center y, and the size. Okay. And we're going to have whatever we do here is going to be duplicated. So there are 4 of them. I'll probably wind up, after I fill in one of these, copying and pasting it. So how do we determine the cx, the cy, and the size? Well, for one thing, you'll note that the size every single time goes down by a factor of 2 from the parent. So if our first node was this big across, its children are half that size. So turns out, because I don't want to have to calculate this over and over, I'm going to make a variable called h size, which is 0.5 times size, and that's what I'm going to pass in there. What about for these others? Where should the center locations be? Well, the center locations are going to be offset by a quarter of the size. So half of the size takes you all the way to the edge. We're going to have one where the x is incremented by half a size and the y is incremented, another one where the y is decremented, another one where the x is decremented but the y is incremented, and then so the 4 combinations of incrementing and decrementing. And I'm going to make another val here. Q size is 0.25 times size, so that I can set cx plus Q size, and I'll copy that. But these won't all stay pluses. In particular, I'm going to make it so that those two go negative, that one's negative, and that one's negative. Okay, so now I have the 4 different combinations. The only thing that's left is the points. So how are we going to do this? Well, I only want to pass through the points that are actually in the square that is centered at that with that size. And so I'm going to make what I want to do is I want to take P and I want to filter, I'll just call it P2. So I'm going to filter out only the points called P2 where, in fact, you know what, there's a part of me that doesn't, I'd really like to call that P. Let's call this one PS to at least imply there's a plural aspect to this. Okay. P rocket, and then I'm going to make a new rectangle 2D dot double. Let's see if that imports properly. Is it because I'm not passing anything? Okay, that's fine. Dot contains P. Yes, okay, so now we just have to pass in the parameters. So in this case, our center location is positive in the x, it's positive in the y, and I'm supposed to, in the rectangle, we give it the top left corner, not the center. So I can't just take these 2 values. But in this case, the top left value for this is cx plus h size, cy plus h size, and then h size is the size of the rectangle. And what is this unhappy about? Overloaded method contains alternatives, cannot be applied to gotcha. Contains P0, P sub 1. Is that actually, okay, that'll work. Okay, so let's copy this code and see how it varies on these others. So in this case, it's cx plus that, but cy minus. Well, the beginning of that rectangle is just at cy, because we're moving positive back up to get to the top left corner by a quarter size. In this case, it's the x that that comes off where the addition is going to come off. And here, it's both. Okay. So, this all compiles. We've taken long enough here to build the tree. Theoretically, this builds the tree. We'll have to do testing on it. We need to still write the code that actually visits the neighbors based upon the tree that we've built. We'll do that next video.